Okay, so this is lesson 3 in our remote teaching of fundamental particles, and this one I've called the forms of beta decay. Now, we've already met two different forms of beta decay, beta minus and beta plus, and we've also already met the idea that there is such a thing as a weak interaction. And the weak interaction is mediated by exchange particles, and these three exchange particles for that do the weak interaction are called the W plus, the W minus, and the Z0 bosons. Only two of them, the W plus and the W minus, are a big deal in our course. The Z0, you just have to know that it exists. And I've used the word massive here. And where I've used the word massive, I mean its proper meaning, got a lot of mass. The Z0 is a huge mass. It's sort of the mass of a gold atom. Massive as in having lots of mass. And as we met in the last lesson, the mass of the exchange particle determines the exchange's range. And because these have got a very large mass, the range of the weak interaction must be really short. Now, if you notice that the sound has changed, that's because I had to come indoors because it had just started raining, which is just about the first rain we've seen this Easter holiday. Anyway, so moving on to neutrons and protons. Now, I mentioned that the fundamental particles have rest energies in MeV on your data sheet. And if you look closely, you can see that the neutron is a bit heavier than the proton. Therefore, the neutron must be unstable. And it turns out that a neutron on its own will decay into a proton. It will do beta minus decay. Neutron to proton plus electron plus antineutrino. So only when it's free. If a neutron is in the nucleus, it's in the nucleus because it's required to be in the nucleus, and the energies of the nucleus stabilize it. And so within a nucleus, the neutron will last forever. We know that. We're pretty confident that some of the helium atoms that are around now are around right to the very beginning of the universe. And so they contain neutrons, so the neutrons are stable. But free neutrons are unstable, and they have a half-life of about 611 seconds. That's problematic. You can see it's not problematic in energy terms, I hope, because you can see that the neutron's about 1.5 MeV heavier than the proton. And in order to create the electron, it only needs half an MeV, which means that there's about an MeV left over for the Ke of the two. 1 MeV left over for the Ke of those two being fired out. So that bit's all fine. And we know that beta minus does charge conservation and electron family conservation and all of that kind of stuff. Now, the controversy comes from the fact that if you measure the decay from a beam of neutrons, you get one value for the half-life. And if you measure the decay for a set of neutrons held in a magnetic bottle, you get a slightly different version of the half-life. I've got a feeling it's something like 7 seconds between the two of them. And that's incredibly controversial because these experiments are now so accurate that their uncertainties do not overlap. You would sort of hope that if you had the two of them plotted up, you'd have one there and one there, and you could put an average through the middle of the two of them that would go through the uncertainties of both of them, and you'd call that average, whatever it is, 611. But unfortunately, so good now are these experiments that their error bars, their uncertainties, have become so tiny that they don't overlap anymore. And you can't put a line through the center of them and say that we've got an average of 611. And so that's controversial and not well understood, and is one of those things that is perplexing physicists right at this moment. It's one of the things that I've put up as a Scientific American article in the extra reading that is in the shared drive at school, and I've also put into a Google Drive. I'm sure I've shared the link with you in the past. I'll probably share it with you again. And if that's of interest, it's read the Scientific American article all about it, because the Scientific American explains such things really well. So, as I say, that's beta minus. But what we've got to do today is we've got to start talking about the particle interaction diagram. So what does the particle interaction diagram for beta minus look like? Well, we start off with a neutron. And we know that the neutron turns into a proton. Now, we now know it does this via an exchange particle, which is either a W minus or a W plus. And it makes two members of the electron family. The W decays into two members of the electron family. It decays into a real electron and an anti-electron neutrino. So the only question here really is what is the exchange particle? Well, of course, we've got a conserved charge. And if you look at this, charge, it must be conserved there and it must be conserved there. Well, charge being conserved here is easy because we've got a negative electron and a neutral antineutrino, and therefore, well, the input there has to be negative. Over here, not quite so obvious, we've got a neutral neutron going in, we've got a positive proton going out, so the only way that works is if we put a negative particle going out as well, and then the positive particle and the negative particle add up to give us the neutral particle that we started with. And so from that reasoning, we work out that it must be a W minus that is our exchange particle. And you're required to be able to sketch those. There's a better version that I nicked off the internet from somebody else. Now, what about protons? Do free protons decay? Because if you think about it, a proton is also a heavy particle. Compared to our electrons, it's an extraordinarily heavy particle. And so we could theoretically get a proton to decay into a positron, because that's got done charge conservation. Of course, we need to do lepton conservation, or sorry, electron family conservation. Well, that's easy enough. We just make a real electron neutrino. And then we've got an anti-member of the electron family and a real member of the electron family. And so nothing's cancelled. That's all fine. So you can see that that should all work. But where it falls down is it falls down on nucleon number, or nucleon number as I've called it so far. Nucleon number. The proton's a real nucleon, so +1. The electron isn't found in the positron is not found in the nucleus, and the neutrino is not found in the nucleus. So nucleon number is not conserved. So we know that nucleon number must be conserved. We know that nucleon number must be conserved because we know that the proton decay. There has to be a rule preventing the proton from decaying because the proton's heavy. Proton's got a lot of energy. Proton would like to find some way to share that energy out amongst other particles and get to a lower energy state. And theoretically, it could do that via this thing up here. But our nucleon number does not allow it to do that. So I threw in nucleon number in one of the earlier lessons and didn't really explain it. This is why it exists, because we know the proton doesn't decay away. Free protons stay as free protons. There's plenty of hydrogen nuclei that are kicking around in all sorts of things like the middle of stars that do not decay away. And so, excuse me. And so we know there must be a rule, and that rule, I've called it nucleon conservation. This does not happen. However, within a nucleus, in order for the entire nucleus to get to a lower energy state, our proton can transform into a neutron. A proton can become a neutron within the nucleus, because although the proton is going to get heavier by becoming a neutron and therefore more unstable, the nucleus as a whole is going to get to a much lower potential energy level by doing the rearrange. And so if we have something that has, if we have a nucleus that has too many protons and too few neutrons, then that nucleus can rearrange itself by transforming one of the protons into perhaps a less stable neutron, but it increases the stability of the overall system. Now, we've written this one out before, so P2N plus a positron and a real electron neutrino. Now, what does the diagram look like? Well, we're just going to start with a proton this time, and our proton is going to become a neutron. We know there's going to be some sort of, I really didn't draw that well, some sort of exchange particle. It's going to be some sort of W. And the W then decays into a pair of electrons, members of the electron family rather. And so we have a positron. Because that's an anti-member of the electron family, we also have a real member of the electron family, the electron neutrino. So what's the exchange particle here? Well, again, we can just do it by charge conservation at this point here. And charge conservation at this point, we've got something coming in that's becoming something positive and something neutral, and therefore the something coming in must itself be positive. Our exchange particle is a W+. There you go. There's a slightly different one that I've nicked off the web again. I actually prefer the previous one, but you know, beggars can't be choosers when I'm stealing things off the internet because I can't be bothered to draw them myself. Okay, is that it? So that's two different forms of beta decay, neutron to proton, proton to neutron. Is that it? Well, let's go back to potassium 40. I said potassium 40 does beta minus. I said that potassium 40 can also do beta plus. However, you'll notice this number out here. It doesn't do beta plus very much. And the mathematically literate amongst you, which of course I hope is all of you, will notice that those two numbers don't add up to 100. So where is the missing 11%? And that's our missing 11%. It's called electron capture. This electron here disappears to be replaced by an electron neutrino, and in the process allows one of the protons to become a neutron. Bizarre. It's a bit easier if we just think about the diagram. So let's start with the diagram. So it's a proton, and this time we've also at the beginning got an electron. Now that electron is part of our atom, our potassium atom in this case. And how is it that it ends up interacting with our proton? Well, it intersects with the proton's W field. So it interacts with the W's, that's with the cloud of virtual W's. You remember that from virtual exchange, the last lesson. So we've got a cloud of virtual W's surrounding our proton, and our electron intersects with that cloud of virtual W's, and beta decay occurs, or a version of beta decay occurs. Now, how does the electron manage to intersect with our cloud of W's? Because you remember our W interaction is incredibly short range. So how does an electron meet one of the W bosons? Well, the electron meets one of these W bosons because you may remember, if you're paying attention, I said that the bottommost energy level for any atom, it's called 1s if you're a chemist, is spherical. And remember we talked about 1 de Broglie wavelength fitting around it. But I also said that that's a semi-classical view of it, and that the reality is a bit more complicated, and that in reality that circular, spherical rather, 1s shell surrounding our tiny little nucleus is really just a limit within which we'll find our electron somewhere. It's a quantum mechanical thing. Our electron lives somewhere, most of the time lives somewhere within that dotted green line that represents 1s. Which means that very occasionally the electron, or one of the two electrons that resides in 1s, is actually inside the nucleus. We know this is true because when it's inside the nucleus, it's no longer being attracted by the protons, and consequently there's a very slight change to the energy levels from the fact that the electron spends some of its time residing within the nucleus, actually residing within the protons themselves. Bizarre, I know. And that very slight energy shift has been measured, and it's part of what's called Lamb shift, which is a very slight discrepancy between those numbers that are calculated based on the Bohr model and those numbers that are actually measured when you do the experiments on hydrogen. So just occasionally the electrons in the very, very lowest energy level of our atom, and you remember this is potassium, so this has got 19 electrons, so it's got a whole pile of other ones. It hasn't just got the 2 in 1s, but one of those 2 in 1s very occasionally is actually within the nucleus, and when it's within the nucleus it has this chance of becoming close enough to one of the protons for the electron to interact with the proton's W field, for the W to catch that electron and destroy it and replace it with a neutrino. And because we've managed to get rid of a negative charge, we can get rid of a positive charge, making a neutron over here, and we've got rid of a positive charge, we've got rid of a negative charge, and so charge has not overall has not been changed, and so we've obeyed charge conservation. So it's a complicated idea. The bottommost electron, and you need to write this down somewhere, the bottommost electron within the energy shells of our atom, in this case our isotope of potassium, comes close enough for one of the protons within the nucleus for it to interact with the W field. The electron gets destroyed and replaced with a neutrino, and in the process that allows charge conservation for a proton to be replaced with a neutron, and that's electron capture. And we have to ask ourselves, what W is involved? Well, of course, I hope it's not too hard. If you see that leaving from here, we must have a positive charge, because we've got a positive charge incoming, we've got a neutral charge outgoing, therefore we've got to have a positive charge going up there. And double check that works over on this corner as well. We're incoming, we've got a negative charge, that negative charge meets an incoming positive charge, and the outgoing is a neutral charge. Yes, that works, and therefore our exchange particle in this situation must be a W+. So that's electron capture. That's an atom destroying one of its lowest lying electrons within its shells in order to allow charge conservation to happen and allow a proton to become a neutron and allow that nucleus to rearrange itself to a more stable state. And you can see why there's an advantage to this over beta plus decay. You can see why our potassium might be able to do beta plus decay, and it can do it sort of, what did I write, 0.001% of the time, but 11% of the time it's going to do this instead, because this is energetically easier, because it doesn't have to find the energy to make an electron. It gains energy from destroying an electron. It gains half an MeV, 0.511 MeV, from getting rid of that electron, and that 0.51 MeV can contribute to the extra mass of the neutron. We know the neutron is 1.5 MeV heavier than the proton, and the kinetic energy of our neutrino. Now that mass of the electron is not enough to do that by itself, and so there's got to be also an energy coming from the rearrange of the potential energy of the nucleus. It can't just do that by itself. The electron doesn't have enough rest energy to drive it, but it helps. It's a whole lot easier to destroy an electron and have its energy available to you than it is to have to create a positron, which is the opposite version of electron capture. The other, which is beta plus decay, the other way that a proton can become a neutron. Electron capture is the more favourable path. So no surprise that our potassium only very occasionally does beta plus, and the rest of the time does electron capture instead. There you go. So there's a better diagram than mine of what's going on. And notice that the W's are angled upwards. There's an upward angle to my W there, because of course this axis here is time. So that upward angle tells you, that little upward wiggle there tells you that the W plus is going in that direction in terms of time. Right, let's just check the other things about electron capture. So you remember that what we need to do is we need to check out all of our rules. So let's just check out charge. That's 1 plus, that's 1 minus, going to 0 plus 0. 1 plus 1 plus 1 minus does indeed make 0, and so yes, that works. Let's check electron family, electron number. Proton's not an electron. An electron is a real electron. A neutron's not an electron, and that's a real electron neutrino. So yes, electron number works. And let's just check out nucleon number. I've said before that that's always pretty trivial. Nucleon number. Proton is a real nucleon. The electron is not. The neutron is a real nucleon, and the neutrino is not. Yes, that one works as well. So there you go. All of our numbers work for electron capture just the same way that they work for beta plus. It's just that electron capture is a lower energy route. Providing there is an electron available to be snagged by the nucleus, then this is the lower energy route. But of course, if you suddenly make a hole in the bottom of your shells, then your electrons have to rearrange themselves. One of the higher energy electrons will drop down to fill up that gap that you suddenly created by destroying one of your lowest level electrons. So one of the ways we can tell whether electron capture has occurred is you get X-ray emission. You get a couple of X-ray photons being kicked out as the electrons within the nucleus rearrange. Now you may be thinking to yourself, why X-ray? When we did hydrogen, an electron dropping down from the higher level to a bottom level would only be in the ultraviolet, it would not be in the X-ray. But of course, remember we're now talking about potassium, which has got 19 protons within the nucleus, and therefore the attraction between the nucleus and the electrons is that whole lot stronger, and therefore the energies involved are that whole much higher, which just pushes us slightly into the X-ray range rather than the ultraviolet range. So they're soft X-rays, or they might be called hard UV or soft X-ray. So they're not very far into the X-ray spectrum, but the electrons are just being attracted enough that the energy levels are now energy levels that will create X-ray photons, not energy levels that will create UV photons. If an electron was to drop from a very high energy level all the way down to the bottommost energy level, or do it in 2 or 3 steps, and we'll get again some X-rays. So we can tell when we've got electron capture because we look for the X-ray emission. Now, electron-proton collision. This is specifically on your course, and I've never really understood why. I can't find any literature about this. Sort of various physics teachers go online and various forums and ask about this. No one really knows why it's there. I think the reason it's here is because our course, our particles part of our course, finishes in the 1970s. And so electron-proton collision was what was going on in the 1970s. Let me just bring, there you go, there's the formula. Now, I hope you're looking at that formula and going, that's absolutely identical to the one I've just copied down for electron capture. And it is absolutely identical to the electron capture. That's what makes electron-proton collision such a difficult idea. I think what's going on is that in the 1970s, which is when our course ends, the best they could do with a particle collider was accelerate electrons round and round the ring until they got faster and faster and faster and getting close to the speed of light and really significant energies. And then what they would do is they would crash those electrons into a target with a lot of protons. You know, just any old bit of metal, really, a bit of metal can have a lot of protons kicking around in it. And so our really high energy electrons are being accelerated round by going around that ring. You know, that 27 kilometre long ring at the Large Hadron Collider. Well, back in the 1970s, that 27 kilometre long ring contained electrons, not protons, because they didn't have the technology to do it with protons back then. So they only did it with the much lighter electrons. And they didn't have the technology to have two beams going in opposite directions. So they didn't crash the electrons into each other. What they did was they crashed the electrons into a target. And so what we've got here is we've got really, really high energy electrons. I know that sounds a bit bizarre because we've been talking all along about electrons as having, you know, the smallest energy of all of our particles. And here I'm saying they've got massive energy. But that's because of the rest energy. The electrons have got a tiny rest energy compared to all the other particles. But if they've been accelerated and accelerated and accelerated until they're close to the speed of light, they've now got a total energy that can be huge. Hundreds of MeV. Because they've got close to the speed of light. And as I said to you previously, when you're travelling at the speed of light, your mass changes. So our electrons can have massive energies. They just can't have massive rest energies. They can have massive energies if they're not at rest. And so that's what's going on here. What we've got is we've got an electron incoming with a whole lot of energy. We've got a proton with not so much energy. It's sitting still. This time, the electron is our high energy one. And our proton is actually sitting in a perfectly stable nucleus. So there's no incentive at all for the proton to change. Nevertheless, our electron has got such huge amounts of energy, it's travelling at such huge KE, that if our electron strikes our proton, it's going to get rid of some of its energy. And striking our proton means interacting with our proton's W field. Except this time, it's going the other way, because the energy to make the W is coming from the electron. It's the electron that's firing out the W towards the proton, because the electron is the thing with all the energy. Our proton hasn't really got any spare energy. It's sitting perfectly happily in a perfectly stable nucleus. The proton has no spare energy. The energy for creating our huge great W and for driving this change is coming from our electron. So our exchange particle is going the other way. Really, I should have that angling up very slightly. I haven't drawn that brilliantly. Let's see if I can rub it out and draw it slightly better. So my exchange particle should be angling up slightly to indicate that it's going forwards in time in this direction. It strikes our proton. It causes our proton to turn into a neutron, gets rid of some of its energy by causing our proton to turn into a neutron. And in order for all the things like charge conservation, things like that to occur, then our electron turns into a real electron neutrino. So electron-proton collision is the same thing as electron capture, except this time the energy comes from the electron. The electron has been accelerated up to massive energies in a particle collider, and therefore the electron is the one now with the energy, and therefore our W originates with the electron. So we have to ask, what kind of W is it? Well, if we look at this corner here, we've got incoming negative outgoing neutral, and therefore where's the negative charge gone? It must have gone off over here, and so this must be a W minus, and we just check that over here. We've got incoming positive, it meets a negative, and the combination makes neutral. Yeah, that works fine. Okay, so there you go, electron proton collision. The W goes the other way. Can't find any literature on the web about this. There's nothing about this apart from on your course, and it's very specifically on your course. And so I'm only guessing, but I'm pretty happy that my guess is probably right for what's going on, for the explanation that it happens when electrons have been accelerated to high energies in particle colliders. And again, there are not many pictures of it on the web because I can't find anything about it on the web apart from for your course. So I've nicked this picture from Student Room, where somebody's put it up on Student Room when they were trying to explain electron-proton collision from your course to somebody else on Student Room. So hence it not being such a good diagram as all the previous ones, because just someone's knocked that up and put it on Student Room in order to help out in response to somebody's question. Now, if you're finding this hard, and you probably are finding it hard the first time you go listen through it, then you could actually choose to stop here. Just skip forward to the summary, because what I'm going to carry on with is, I hope, really interesting and useful in thinking about how these diagrams occur and thinking about the different kinds of beta decay, but they're not necessary. The 4 diagrams I've drawn over these last 4 little things, they're the ones that are necessary. You have to be able to reproduce those diagrams. You have to be able to reproduce these equations. You have to be able to reproduce the diagrams for the 4 interactions that I've discussed so far. So the 2 that I'm going to discuss next are not on your course. So like I say, if you're finding this hard, you can skip ahead. I hope you're not going to skip ahead, but you can skip ahead. Right. I hope you've been thinking this. How do we know neutrinos exist? It's all very well for Pauli to go, there must be this other particle, and for Fermi to go, oh, it's a little cute neutral particle, therefore it's a neutrino. But we've got to, we're physicists, we need a bit more than that. How do we know that they exist? Especially since when Fermi, because although the idea was originally Pauli's, it was Fermi who wrote out the theory. When Fermi wrote out the theory, a couple of more mathematically minded physicists, I have no idea how to say that, or that in truth, they calculated that if Fermi's correct, then these neutrinos are going to pass all the way through the Earth and only very occasionally actually collide with anything. They can go all the way through the Earth without interacting. They're weakly interacting. We've mentioned this already. And Fermi's theory and their calculations within Fermi's theory just reinforce that that's true. And so how the hell do we find neutrinos if neutrinos can go all the way through the Earth without hitting anything? So we have to jump ahead in time a little bit to the 1950s. These 2 chaps, Cohen and Reines, proposed that, well, if you have enough antineutrinos being created, and nuclear reactors actually make a lot of antineutrinos, and you pass them through a lot of protons, then occasionally those neutrinos might force inverse beta decay. And then this is inverse beta decay written out at the bottom here. And so inverse beta decay is a proton being struck by an antineutrino and becoming a neutron and a positron. Now, I hope you've been paying enough attention to realise that that's energetically difficult, because our proton is 1.5 MeV lighter than our neutron. Our positron is half an MeV lighter than our antineutrino. So we've got to find at least 2 MeV for this to work. Or, I'm sorry, I've said specifically 2 MeV, but it turns out to be a little bit less than that when you actually do the maths. But you've actually got to find 2 MeV or more, because you've got to have enough kinetic energy for our positron that we create. So we're going to need quite energetic antineutrinos. Well, that's all right. It turns out that some of the antineutrinos created in a nuclear reactor actually are quite energetic. And so Cohen said, well, if we've got a nuclear reactor that's pumping out enough really energetic antineutrinos, then we may well actually get this inverse beta decay occurring. If we just check it out, that's a proton becomes a neutrino, so that's nucleon number, that's fine. We've got an anti-member of the electron family becoming an anti-member of the electron family, so that's electron family or electron number, that's fine. And finally charge, that's 1 plus 0 to 0 plus 1 plus, and so charge is fine too. So yeah, this inverse beta decay should work. We just need nice energetic antineutrinos, and we need a lot of them. So we have Cohen-Marin's experiment, which they conducted in 1953. So we've leapt ahead of time a bit here. The neutrino was being proposed in the 1920s, and the experiment to prove it existed didn't happen until the 1950s, but of course you realise sort of world events intervened. Now, eventually they used a nuclear reactor that was producing 5 times 10 to the 13 neutrinos every second, every square centimetre. So a lot of antineutrinos. Should have written antineutrinos there, shouldn't I? And they set things up so that this nuclear reactor was pumping its neutrinos out through tanks of water. Because if you think about it, water has a lot of protons. Water molecule is essentially 2 protons sticking off the end of an oxygen atom, because the electrons associated with the hydrogen atom get taken up by the oxygen, and so we get 2 protons sticking off the side of an oxygen atom, and so water's got loads of protons, and so 200 litres of water, and then within the water they dissolved cadmium chloride. Now, why was that? Well, they wanted to be sure that they would detect the inverse beta decay when it occurred, to actually show that the neutrinos really were forcing the water to change. And they had a couple of thoughts about the detection. One is this positron. Now, we've not done annihilation yet, but you probably know enough about annihilation to know that I'm going to fight my cat here. You probably know that enough about annihilation to know that our positron, when it meets a real electron, the 2 of them will annihilate each other with the production of gamma rays, while it produces 2 gamma photons. So as soon as you've got inverse beta decay going on inside your water, those positrons are going to go off and hit any electrons that are kicking around, and we're going to get a pair of gamma rays come out. But Cohen said, well, if we detect some gamma rays, that doesn't really prove that it's inverse beta decay that's going on. So what they suggested was, why not put in some cadmium as well? Because if cadmium meets a free neutron, it will absorb it and make cadmium 109. And there's a little, I don't know how well you can see that there, there's a little star there, and the star is there to indicate that the cadmium is excited. So when the cadmium nucleus absorbs our neutron, it does so in an excited state. That nucleus wants to get back down to ground state, and so it gets down to ground state by emitting a gamma photon. And so what Cohen said is there's nothing else that's going to do this. The only thing that's going to produce 3 gamma rays for every event is this inverse beta decay, because we've made a free neutron, we've made a neutron that all of a sudden isn't attached to anything and is available for the cadmium to absorb, and we made a positron that's going to annihilate and produce a pair of gamma rays. And so we're going to get 3 gamma rays every time we get this event occurring. We get 3 gamma rays, and if we set this experiment up and we see these sets of 3 gamma ray coming out, then we know anti-electron neutrinos must exist. So that's just 2 gamma rays from the annihilation and the 3rd from the absorption of the neutron. And scintillation detectors are things that flash when they're hit by gamma rays. So there's the diagram for it. We have an incoming anti-electron neutrino, meets the W field of a proton, and the W plus is exchanged, and we get a neutron and a positron coming out. And I wasn't absolutely certain which way the W was going, but the W is going that way. You don't have to be able to reproduce this diagram. So this is their thinking. High antineutrino flux from their nuclear reactor, passing through their tanks of water. If they spot events where they get 3 gamma rays all at once, then they've almost certainly got antineutrinos. So it's their proof that antineutrinos exist. And the result was they got about 3 sets of 3 gamma rays every hour. Turn the nuclear reactor off, these 3 gamma rays together stop happening. Turn the nuclear reactor back on again, and they start getting these 3 sets of events, 3 an hour. So that allowed them to do some calculations. Before they did the experiment, they'd calculated that the likely reaction cross-section, so reaction cross-section is how big a target does our proton present to the neutrino. And they'd said that our proton presents an absolutely minuscule target, 10 to the minus 44 centimeters squared. Stupidly tiny. I don't know why it's centimeters squared. It's because I'm using Wikipedia to get these numbers from. So they calculated 6 times 10 to the minus 44. They measured 6.3 times 10 to the minus 44. So perfect science, really. You have a theory to explain something unknown. So we couldn't before explain why it was that we were missing energy from beta decay. Pauli theorizes the existence of an extra particle. We develop a theory. Fermi develops a theory for the behavior of this extra particle. Cohen and Reines develop an experiment to test the theory, and they then conduct the experiment, and the experiment backs the theory up. They get 6.3 when they were expecting 6 on the basis of the theory. So those results get published in one of the most prestigious. There's 2. If you're a scientist, there's 2 journals you want to be published in. You either want to be published in Nature, which is the British one, or you want to be published in Science, which is the American one. You're publishing one of those 2, basically you've made it. Did they get a Nobel Prize for it? Well, Reines did, because Cohen died before it was issued. I don't know why it took so long. That's 40 years. Goodness knows why it took 40 years for the Nobel Prize Committee to recognise their work. And you can see most of the stuff I'm talking here, I'm taking off Wikipedia, and I took that off Wikipedia as well. Okay, so that was inverse beta decay, and that was proving the existence of antineutrinos. You're saying to yourself, but how do we know that antineutrinos are different from real neutrinos? Well, for that we come to a different experiment and a different problem. And it comes down to the existence of solar neutrinos. Now, ever since you were in primary school, you've been told that the sun fuses hydrogen and helium. So you've been told that that is nuclear fusion. But of course, you're older and wiser now, and you know that 4 protons, because of course a hydrogen nucleus is just a proton, 4 protons do not make 2 protons and 2 neutrons. 4 protons do not make a helium nucleus. So you know that there's something else going on in nuclear fusion. But you see, you're wiser still now because you've just watched this this video, and you know it's perfectly possible for protons to turn into neutrons, providing they do beta plus decay. So 4 protons can indeed become a helium nucleus, providing that in the process 2 of those protons have done beta plus decay to become neutrons. And if 2 of those protons have done beta plus decay to become neutrons, then we must create a couple of positrons, and we must have created a couple of real electron neutrinos. Now the positrons, they're going to bump into electrons that are kicking around within the star. They're going to annihilate. But Our electron neutrinos, as we've been discussing, neutrinos don't interact, so our electron neutrinos, the vast majority of them, are going to get out of the star. Blah, 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 blah. So this process here, most of the protons become neutrons in the process of the two protons colliding with each other and making deuterium. Deuterium is one proton and one neutron, and so we get the beta plus going on in the process. And that energy releases neutrinos with a total kinetic energy of 400 keV, or 0.4 MeV. But there are other processes that go up to 18 MeV, so we get a whole range of neutrino energies from the sun, most of them at 400 keV, but others go right up to 18 MeV. Now, this bit is just jaw-dropping. If you can look at that and not have your jaw hit the floor, then you haven't understood. The neutrino flux at the Earth is about 70 billion, that's what that says, 70 billion. 70 billion particles passing through every square centimetre every second. And that's at the Earth. The Earth is 150 million kilometres away from the sun. The sun is firing these neutrinos out in every direction. And if you took a sphere around the sun with a radius of 150 million kilometres, every square centimetre of that sphere would have 70 billion neutrinos passing through it every second. Oh my God. Now, you've done a little bit of those calculations in the introduction to A-level physics booklet that I made for you. And so you've done some work with the numbers involved with the sun. You've worked out how big those numbers become so very, very fast. And so maybe this isn't such a big surprise to you, but crumbs. As you sit there, what cross-section are you presenting to the sky? I don't know, a few hundred centimetres squared. So that would take you up to sort of trillions of particles, trillions of neutrinos passing through you every second. That's just amazing. Right, if you're a physicist, of course you want to prove this is true. You want to detect these neutrinos. And how do you detect these neutrinos? Well, as you've already read, the answer is chlorine. Chlorine's got two stable isotopes. If you're a chemist, you know that chlorine's atomic mass is 35.5. And that 35.5 is because chlorine on Earth is made up of these two isotopes, chlorine 35 and chlorine 37. And on Earth, not necessarily the same everywhere else, but on Earth, they're in the ratio of 76 to 24. And if you combine those together, you get 35.45, I think, actually, as the sort of average atomic mass of chlorine here on Earth. So, why no 36? You're asking yourself. Surely there must be a 36. And if there's a 36, how is there's a 37? Well, you probably realised that the 37 can't be all that stable. It is stable, but it must be marginal, mustn't it? It doesn't do decay, but it must be marginal, mustn't it? And it turns out that if you hit chlorine 37 with a real neutrino, that will allow our chlorine to turn into argon and spit out an electron. So it's called neutrino capture. Another form of beta decay, neutrino capture. So our chlorine can go through a decay and become argon, but it won't do it naturally itself. It hasn't got enough energy to do it naturally itself. It has to get some energy from the neutrino. How much? The answer is 0.8 MeV. So the majority of the neutrinos passing through the Earth won't do the job, because we've already said that most of those are at 0.4 MeV. But it turns out that there are a lot with about the right energy that come from the decay of beryllium-7. It turns out that beryllium-7 is really, really important in nuclear fusion. So there's loads of beryllium-7 decaying away within the sun, being manufactured and then decaying away. It's part of the process that makes helium in the sun. And the neutrinos that are emitted from the decay of beryllium-7 are just the right energy to force the chlorine to shift into argon. Bizarre things we've discussed today, isn't it? The idea is perfectly stable chlorine, hit it with a neutrino, this almost made up particle made up by Pauli, hit it with a neutrino with enough energy and it will become argon. Now, how do you detect that? Well, of course, argon is an unreactive gas. So if we have our chlorine in a compound, if some of the chlorine gets hit by neutrinos, that'll form argon. The argon will no longer be part of that compound, and we'll have argon gas. We can measure how much argon gas gets made. It's a bit like radon as one of the decay products of uranium. Of the radon escapes because it's an unreactive gas. The uranium is part of the rock, the radon isn't. Anyway, I digress. So if we have enough chlorine, 24% of that chlorine is going to be chlorine-37. There's a lot of neutrinos going through that chlorine. Some of those neutrinos are going to form argon. So, neutrino capture. There's the diagram. Neutron becomes a proton, but this time the energy, the incoming, is a real electron neutrino, and we get a W minus, a W minus, and an electron. Didn't draw that very well. Good job. There's this diagram over here. The only problem is it uses the beta symbol there instead of an electron. So neutrino captured by the neutron turns into a proton and emits an electron, and it's a W minus is the exchange particle. Just check that it works. Neutron incoming, positive proton outgoing. So the only way that works is if it also spits out a negative particle, and therefore that must be a W minus. Yep, that works. So where did they perform this experiment? Well, they did it down a gold mine. That's why it's called the Homestake experiment, because it was done down the Homestake gold mine in South Dakota. I don't know why the name South Dakota amuses me, but it does. And this gold mine, as most gold mines are, was incredibly deep, 1.5 kilometers underground. Why did they do it down in the gold mine? Well, all neutrino experiments were done deep underground, because if they do them deep underground, it's only neutrinos get in there. All the other cosmic rays and things don't get through the 1.5 kilometers of Earth. But neutrinos, they easily go through the 1.5 kilometers of Earth. And so you're pretty sure if you build something deep underground that the things you're measuring are going to be neutrinos. And what did they use? Well, they used dry cleaning fluid. Now, a meter cubed is 1,000 litres, so that's 380,000 litres of dry cleaning fluid. They used dry cleaning fluid because it's commercially available. They must have got some raised eyebrows when they went to the dry cleaning company and said, we need 380,000 litres of your dry cleaning fluid. But dry cleaning fluid is just tetrachloroethene, and of course, if you're a chemist, you know exactly what that means. As far as we're concerned, it means 4 chlorines. So 4 chlorines, one of those chlorines is probably going to be a 37. So one of those chlorines is available to be turned into argon if it's struck by a real neutrino. Every few weeks, they would pop along and they would bubble helium through the liquid, and the helium would cause any of the argon that happened to have been formed by the neutrino capture to bubble out as well. Then they take the helium off, separate out the argon from the helium, and measure how much argon has been formed over the couple of weeks it's been sitting there. And their conclusion was a problem. We know what the sun's up to. We're pretty confident we know what the sun's up to. The stars actually are pretty uncomplicated things. So we can work out almost exactly, based on how much energy comes out of the sun, we can work out how many neutrinos must be coming out of the sun. And so this result was a shock. They did indeed get argon being formed, but they got almost exactly 1/3 of the expected amount of argon. Difficult. And this discrepancy became known as the solar neutrino problem. And there still is a solar. They think they have an explanation, but it's still incredibly controversial, and it's still a big part of neutrino physics today. It's actually really important right at the moment. And so there's all sorts of experiments being designed and theories being written about what's going on with neutrinos that all basically come from this homestake experiment. And it's another of the things that I've found. I've scanned a couple of copies of I'll try that better. I've scanned a couple of articles from Scientific American, and I've put them into the reading because, if you're interested in this stuff, this is really, cutting edge physics that's still being argued about what's going on here with these neutrinos. Okay, that's it. You can tell that I'm wilting, and I guess you're wilting too, but you've got the advantage of being able to pause this and go back and watch it again. In summary, the weak interaction is responsible for beta decay. The weak interaction exchange particles, W+, W-, Z0, only the two W's are of interest to us, and quite often they're written like this to indicate the two of them. Beta decay comes in different times. We've met two of them before this. One of the forms of beta decay is when free neutrons decay to become protons. But protons do not decay. Protons are stable. So neutrons are unstable particles. Neutrons do decay, but only when they're outside the nucleus. There are 4 kinds of beta decay that are required for the course. You have to be able to reproduce the equations for them, and you have to be able to reproduce the particle interaction diagrams for them. So the first 4 that I went through in this display, not the last 2, the first 4 are required for the course. They are beta-, beta+, electron capture, and electron-proton collision. Now I've also given you lots of other things to think about here. A couple of big controversies in physics, the solar neutrino problem, for example, the 2 different decay times for the neutron. Some really big current problems within physics have turned up as part of this talk. So I'm hoping that you're interested enough to go away and look up some of that stuff and do a bit of thinking on your own. But the important stuff is this. If you've not noted all of this stuff down as you've been watching this video, then you've got to go back and you've got to write down how these 4 beta decays work, and you've got to write down the equations for these 4 beta decays, and you've got to draw the diagrams for these 4 beta decays. And you've got to be able to reproduce them in the exam. Doesn't come up hugely often on the new course, came up all the time on the old course, doesn't come up as often as on the new course, hasn't really come up yet, which probably means yours is the year when it will. So therefore, have to get this done, please. So go back through the video, copy down the equations and what's going on for the various forms of beta decay, those 4 forms of beta decay, not the last 2. Not inverse beta decay and not neutrino capture, and make sure you can draw the diagrams for them. Okay, see you next time.